In this section, we'll be talking about quadratic functions. Quadratic functions are just one branch of an overall family of polynomial functions, some of which we've studied in the past. Let's put the polynomial functions in perspective just for a moment, and then we'll get on with the matter at hand. These are polynomial functions. They are called polynomial functions because the expression used to describe them are polynomials. Now, notice the notation over here. It's customary in mathematics for letters at the front end of the alphabet to stand for real numbers, and letters at the back end of the alphabet like X, Y, and Z to stand for variables. So here, A, B, C, and D stand for real numbers. X is the variable involved. Now, the difference among these polynomial functions is in the degree of the polynomial expression. This is a 0-degree expression, first degree, second degree, third degree, and so on. We have studied 0-degree polynomial functions, if you will. They're just constant functions. It would be like f of x is equal to 2. And we know all about the graph of y equals 2. It would be a horizontal line going through y equals 2. We've also studied first-degree polynomial functions, linear equations, you see. And we know that in this form, if we see a polynomial function in this form, we can read its slope and y-intercept, so we can describe the behavior of the graph rather easily. Well, now we're talking about quadratic functions, and that's this rascal right here, second-degree functions. And later we'll be talking about third-degree polynomial functions and beyond. Well, we've actually seen polynomial functions of the second degree, that is quadratic functions, before, and we saw them when we talked about transformations. Now, remember at that time, transformations can either be rigid or non-rigid. Rigid transformations were transformations or changes in graphs that kind of move left, right, up, down, or maybe we have a reflection of one kind or another. Non-rigid transformations are transformations that really change the shape of the graph. It causes the graph to either be sort of compressed or thinner or maybe expanded like this, kind of fatter a little bit in the curves. Well, let's review that just a little bit. We looked at situations where we might have an equation like this. And we can think of this as f of x equals this expression or y equals this expression. Doesn't make any difference. But recall at the time that we were identifying a prevailing operation, and in this case it's squaring. And we know that the squaring operation leads to a graph which is a parabolic curve. All right, now our various transformations arise by virtue of the various numbers that we see here. When we have an addition or subtraction of the variable before the squaring operation, then the transformation, it's rigid, is left or right, but in a direction we don't expect. If we see x minus 3, then the graph actually moves plus 3 on the coordinate plane. Now, this is the graph of y equals x squared. Okay, when we talk about x minus 3 squared, then this graph moves 3 to the right. Now let's just identify the position of the vertex, the change in the vertex. So the vertex would go from here, 1, 2, 3 to the right. And the rest of the graph would be like this. All right, now what about the 2? Well, the 2 means that the graph will be relatively thinner. You see, just a little bit thinner like this because we're sending those vertical distances up the coordinate plane twice as fast as they were before. That's one way to look at it. Now, the negative on 2 means we want the opposite of all of these vertical distances, and so we have a reflection then in the x-axis. So now we have a parabolic curve that opens downward and is relatively thin. And then minus 1 sends the whole graph down 1 on the coordinate plane. So it kind of looks like this. Okay, so that was the idea. Now, the vertex of a parabolic curve is either the topmost point or the bottommost point on the curve. Now here, for this one, it's the topmost point. So this is the vertex. And it turns out that the coordinates of the vertex can be found by looking at this form of the function. That is, our vertex here is at the point 3, negative 1. And notice we have 3 here and negative 1 here. Now notice that the 3 is a number that follows a minus sign. So the coordinates of the vertex can be found in this form. Now, this form of a quadratic function is called the standard form. And it's called the standard form because we have information about graphing with standard forms. The general form is the expanded form, and it's that expanded form that we looked at in this list of various polynomial functions earlier. So we have a standard form then for our quadratic function, and it is this form, and the vertex can be identified at hk, and h follows a minus sign. All right, that's very important. It accommodates that idea of the shift happening in a direction we don't expect. If we just realize that the h follows a minus sign, it takes care of itself. Now, let's talk about going from the standard form into the general form. All we really have to do to go from standard to general is expand and collect like terms. So here, with this expression, if we expand, it means we first square the binomial. We get x squared minus 6x plus 9. And then minus 2 times all of these, and then collecting with the negative 1, we get this. So this then is the general form for our quadratic function that we started with. Now, standard form, general form to standard form. You know, if we can go from standard form to general form rather easily, can we not go from general form to standard form? That's the real key, because we don't have information about graphing when we just look at a general form. We have that information when we can change into the standard form. Let's look at that process. Here we have a function g of x is x squared plus 8x plus 11. Now, you know the standard form involves having a binomial squared and then followed by perhaps some constant. Well, because we are creating a situation where we want a binomial squared, we go through the process of completing the square. We are completing a trinomial square so that we can factor into a binomial squared, and we begin the process by rewriting in a way where we leave a vacancy for the constant term and just kind of kick this out a little bit. Just move that over. And here's how we're thinking about it. You see, like this. And we want to reinvent the constant that goes here. Well, we identify that constant as half of this coefficient, half of the coefficient of this term, squared. Now, the coefficient in this term is 8. Half of 8 is 4. 4 squared is 16. So we'll add 16 here. But we are causing an imbalance in the equation. Now, in some circumstances, mathematically, when we go through the process of completing the square, if we add an amount on one side of the equation, then we have to add it on the other side of the equation to maintain the balance. But here, we're confined to this side of the equation. We want g of x over here, and we want to leave it over there. We don't want any other business over here. So when we add 16 here, we have to subtract 16 on the same side of the equation to accommodate that. All right, now we can rewrite. Factoring here, we get x plus 4 squared, and then collecting out here, 11 minus 16 is minus 5. So now we can easily imagine the graph. We could use this transformation idea to imagine the graph if we want to. I mean, think about it a little bit. If we just kind of look at it from what we knew before we got into this section, we would have a horizontal shift of 4 places in a direction we don't expect. Let's see, it says plus 4, so we go to the left 4, and here's our vertex. And then minus 5 takes us down 5, and we're in this position. Now, because this coefficient here is just an understood 1, it means that the shape of the parabolic curve is normal. That is, it kind of looks like a regular old ordinary everyday household parabola instead of being kind of fat or kind of thin. Okay, so it kind of looks like this. Now, if we were using the HK idea, it's very similar. I mean, the HK, here's the H, here's the K. So H is, wait a second. H was a number that followed a minus sign. So we have to think about this in a rather creative way. We have to really think about this as x minus negative 4 squared, kind of like this, then minus 5. So the number that follows a minus sign is negative 4. So we have a vertex at negative 4, negative 5, which is what we found here. Okay, so we can read it in. Now, you don't really have to rewrite like this, but you need to imagine it in order to identify the coordinates of the vertex. All right, let's go through the process again of going from general form to standard form. This time, though, notice that I have a coefficient of the leading term. Now, this method of completing the square, where we just take half of the coefficient of the first degree term and square it in order to complete the square. That works every time we have a leading coefficient of 1. But here we don't have a leading coefficient of 1, so we have to create that situation like this. Now, we're going to force the factorization of the negative 2. Now, when I say force it, what I mean is we're going to factor that leading coefficient whether or not it's a factor of the second term or not. You see, it may not be that this term is even if we're factoring a 2. And if it's not, we still have to force the factorization. So anyway, a forced factorization. We're going to snag negative 2 out of just these two terms. We don't care about that. We're going to kick it out anyway. So we're going to pull negative 2 out of these two terms, leaving, well, let's see. Negative 2 out of this term leaves x squared. Negative 2 out of this term leaves minus 6x. Okay, now I'm leaving a little space, and I'm putting the minus 19 out here. All right, now we're ready to complete the square. Okay, we complete the square. We're kind of looking in here, and we're completing the square in this parenthesis. Leading coefficient is 1 now, so we follow that prescription we had before. Half of negative 6 is negative 3. Negative 3 squared is 9, so we're going to add 9 in here. Now the thought is that we have to balance the equation because we've caused an imbalance. But notice something here. If we add 9 in this parenthesis, if we add 9 here, what are we really adding to this side of the equation? You see, we are really adding negative 2 times 9. We're really adding negative 18 to this side. In putting plus 9 right here, it really puts in minus 18 into this problem. You see, so we have to go plus 18 out here. All right, very important idea that we look at this, this factorization out here to complete the problem. All right, at any rate, I think that's one of the more difficult things to see and to think about in this whole process. Let's see, we have negative 2, and then the factored form is x minus 3 squared, and collecting out there we get minus 1. So now, let's see, let's use the HK idea. We have a vertex at HK. H follows a minus sign, so at 3, negative 1. And this rascal opens, well, let's see. We have this minus sign out here, meaning that the parabola opens downward, and a 2 means that it's relatively thin. So at 3, negative 1, we have a vertex opening down and thin. Well, we knew this kind of before. This is the one that we started out with. But we started out with it in this form to begin with. But it's no surprise that it ends up here. Let's go through the process again of changing from the general form to the standard form. Consider this problem. Now, this might be a pretty good time to copy the problem and then try the problem on your own and then roll the tape to verify your answer. But at any rate, we begin like this. We think, well, we're going to complete the square, and we know we're thinking about it like this, where we have the 3x squared plus 4x, and we want to invent a new constant term, and we're kicking out the existing constant term, but we have a leading coefficient other than 1. So we need to force the factorization of the 3 out of these two terms, and that's where the trick comes into this problem. So we were thinking this way. We're going to snag 3 out of these two terms. All right, 3 out of this term, no big deal. We're left with x squared. When we pull 3 out of this term, there are two ways to think about that idea. One way is to realize that whatever we write right here, we have to be able to multiply 3 times that item to get 4x. You see, and all we need to do is identify what we're going to multiply against in order to get that. So that's one way to think about it. And in thinking about it like that, you think, well, gee, multiply 3 times something to get 4x. Well, the something right here, it better be a fraction, and we'd better be able to cancel 3 you see, out of that rascal in order to get 4. So we might put 4 in the numerator and 3 in the denominator. You see, kind of like that. So that's the idea. Another way to identify the 4/3 here is like this. We think, well, gee, we want to think about a number, let's call it n, such that 3 times that number is equal to 4. You see, that's really what we're doing. 3 times some number is equal to 4, and we're just identifying the number. Well, let's see. To solve this, we would divide on both sides by 3 and find n to be 4/3. Aha, the coefficient is 4/3. All right, 2 ways to do that. Now, once we've identified that number, the fun isn't altogether over, is it? Because after all, we have to complete the square. Now, to do that, we take half of this and square and put it right here. Okay, we're taking 4/3 and we take half of it. Well, we're multiplying by 1/2, and then whatever we get here, we're going to square. So that's the idea. All right, let's see. The 2 and the 4 cancel, that's 2/3. So we have 2/3 that's being squared. And 2/3 squared, oh, that's 4/9. So we're really adding 4/9 in here. Now, I'm adding 4/9 in here. Let me clean that up a little bit. I can do 4/9 a little better than that. So plus 4/9. Now, although we're adding 4/9 here in parenthesis, what are we really adding to this side of the equation? You see, we're really adding 3 times 4/9 to this side of the equation because it's in parenthesis. So 3 times 4/9, a 3 and the 9 would cancel, leaving a 3. We're really adding 4/3, so we have to subtract 4/3 over here to balance the equation. Now the next challenge is to factor. Well, that's not a real big deal if we keep track of the amount that we squared down here to add in. Here's what I mean. I've got 3 times. Now, the amount squared, you see, it's a binomial, and this is a trinomial square. And when you factor a trinomial square, you get the item that is squared to give the first term, and you get, as the second term, you get the item that's squared to give that. Well, what was squared to get this? Well, it was the 2/3 that was squared to give the 4/9. See, so it's kind of valuable sometimes to keep track of the amount being squared. So it's plus 2/3 squared, and then collecting here, well, let's see, this 4/3 is 1 1/3, so it's minus 1 1/3, that's minus 2 1/3. Well, now we can imagine the graph here. We can think about a vertex at HK. Now, the HK, H follows a minus sign, so we have to think of this as minus negative 2/3. So negative 2/3 for the H, and then the K is negative 2 1/3. And from this position, we know that the graph opens upward because this is positive, and it's really thin because of the 3. So now remember that when this coefficient is positive, the graph opens upward. When it's negative, it opens downward. If this number is larger than 1 or less than negative 1, then it turns out that it's relatively thin. And if it's a common fraction, sort of between negative 1 and 1, then it's relatively fat. Okay, that's the idea. Consider this problem. It says, write the quadratic function whose graph has a vertex at this point and which passes through that point. Well, gee, we're changing gears here quite a bit, aren't we? After all, before we're starting with functions and we're going to graphs. And now we have information about a graph and we're creating the function. Well, it should be no really big deal, but let's understand what we're trying to accomplish. We've got, let's see, we want a quadratic function whose graph has a vertex at this point. Let me sketch that. We have at 2, 3, we have a vertex. And the graph is going to go through. See, right now we don't know whether it opens up or down, but it goes through the point 0, 2. Ah, okay, it goes through this point. So the graph then is going to look like this. And I'm thinking that in order to do that, it looks a little funky, but we get the idea. It's just a sketch. It's going to open down. That means that that coefficient A is going to be negative. And it kind of looks a little fat to me, so it looks like, or I think that the A value is going to be a common fraction. So a negative common fraction is what I'm looking for here. Well, let's see. In our investigative process, we might start like this. We know that the standard form is A times x minus h squared plus k. All right, now what information do we have? Well, we have this. We know that if the vertex is at 2, 3, that this is the h and the k that appears here. So we have A is x minus 2 squared plus 3. All right, we know that much. Now, we can write f of x as y equals A times x minus 2 squared plus 3 if we want to. The trick here is to identify the value of A. Now, how do we do that? Well, it turns out that we use the information about the coordinates of that point that's on the graph. And the way we use it is like this. We realize that this great relationship between the points on a graph and the equation describing the graph. And that wonderful relationship is that every point on the graph has associated with it coordinates. And the coordinates of every one of those points on the graph solves the equation, makes it true. And so if we take the information about the coordinates of that point, that is the 0, 2, as an xy pair, and put it in here, you see, for this xy, then we have an equation that we can solve for, you see, A. So let's do that. I've gone through the problem up here. Here's what we start with. Kind of now, notice I'm using the y form instead of f of x, just for manipulative purposes. And now the h and k are replaced with 2 and 3. And then we realize we're going through a point, so we use the coordinates of that point, and the coordinates are 0, 2. So x is 0, y is 2. Just pop those values in, and now solve for A. This is negative 2 squared, that's 4. So here we have 4A, then plus 3. Subtract 3 on both sides, subtract 3 over here, it disappears, subtract 3 over here, we get negative 1. Divide on both sides by 4 to isolate the A, and we find A to be negative 1/4. Kind of as expected. The A value is negative, and it's a common fraction, so we kind of expected that. All right, then we move back over here, and we rewrite like this. Now, we're looking for a quadratic function. I'm going to go from y back to f of x. You see, and now it's negative 1/4 times x minus 2 squared plus 3 as the quadratic function whose graph has a vertex at 2, 3 and which passes through the point 0, 2. Consider this problem. The perimeter of a rectangle is 400 feet. Let x represent the width of the rectangle and write a quadratic function that expresses the area of the rectangle in terms of its width. Of all possible rectangles whose perimeter is 400 feet, what are the dimensions of the one that has the greatest area? I think this problem may sound complicated because we're involving perimeter and area in the same problem, and that's not often the case. Well, when some confusion arises or when problems seem complicated like this, write down the information that you know that's given in the problem, and also write any relationships that are kind of intuitive. Like in this problem, we're talking perimeter and area, and we know those formulas. So we might start by just writing perimeter 400 feet, width x. Now, perimeter is 2 times length plus 2 times the width. We know the perimeter is 400. And the width is x, and that's about what we know right now. We could write down the area formula if we want to. Area is length times width. But let's understand what we're trying to accomplish here and kind of the nature of the problem. We're given the idea that a rectangle has a perimeter of 400. Now, there are a lot of rectangles that have perimeters of 400. We could think of a rectangle that is incredibly thin, and whose length then would be, let's say, very near 200. So sort of the top and the bottom would both be near 200, and together that's near 400. But if the widths are just really, really tiny, you see, that's very possible. So we could have a really thin kind of rectangle whose perimeter is 400, and then we could make the widths a little bit wider, you see, and then that rascal would kind of come in like this. Now what we're trying to do is find the dimensions of a rectangle whose perimeter is 400 still, but the dimensions of the rectangle which has the largest area. So we're going to write area as a function of the width. Now here's how we do that. We first of all take this relationship, and we need some way of writing the length in terms of the width. So we're going to take this and solve it for L. So we're doing this. We write 400 minus 2x equals 2L. I'm dividing throughout by 2, and I get 200 minus x equals L. Now we have a representation for the length. Now that's handy when we come up here and write the area formula. Area is length times width. And we'd like to write everything in terms of x. So length, we solve for length over here. It was 200 minus x. The width is x. And now we have area is 200x minus x squared. So this is area in terms of width. We could even think of it like this. We could use a notation that is function in nature. It is area in terms of width, like this. You see? A in terms of x, or A of x. All right. Now, we'd like to find the largest possible area given this idea. Now, built into this is the notion that the rectangles that we're thinking about all have a perimeter of 400. That's kind of built in here from what we did just a moment ago with the perimeter formula. All right, so that's the nature of this idea. Let's put this into standard form and identify the vertex, and then we'll analyze the graph. We've got A is, now I want to complete the square, so I'm thinking about reinventing a constant that doesn't even exist right now. So I need to, let's see, leading coefficient needs to be 1. So I'm going to force the factorization of this negative. So it's negative, and now x squared, and then minus 200x. Notice it just served to change the signs. And then vacancy, and then vacancy out here. All right, half of 200, or half of negative 200 if you will, is negative 100. Negative 100 squared, a 1 followed by 4 zeros, 10,000. So I'm going to add 10,000 here. But if I add 10,000 here, oh, wait a second, what am I really doing? I'm really subtracting 10,000. So if I'm subtracting 10,000, I need to add 10,000 out here. So we have to be careful about that and make sure we look at this coefficient when we're considering that idea of balancing the equation. All right, now I can factor. I've got minus. Now let's see. What did I square here? I squared negative 100. So it's x minus 100 squared, you see, that goes in the parenthesis for the factored form. And then plus 10,000. Now, graphically, I have a vertex at hk. H follows a minus sign, so it's at 110,000. What in the world does this mean? We also know that the graph opens downward. So we have a vertex here and the graph opens downward. All right, let's interpret the situation. Let's see, we've got, I need some room here, but I want to keep the L. I'm going to move way out over here. All right, let's see. We've got a graph that has a vertex at 110,000. So let's say this is the point 110,000. It's way up the coordinate plane. And the graph opens downward, but it's relatively normal in shape. So it might look something like this. Now realize what we have here. This is area in terms of width. So all the values out here, although we're calling them x's, they are really width values. And for values of the width, we're getting values up here that are area. You see, so for a width here, we have an area. For a width here, we have an area. For a width here, we have an area. So horizontal distances are widths, vertical distances are areas. Okay, that's really important to understand here because this is the point where a width of 100 gives a maximum area of 10,000. Now, we want the dimensions, that is length and width, of this rascal. Well, how can we do that? We know the width is 100. What about the length? Well, let's see. The length we found over here is 200 minus x. X is the width. So if the width of this rascal is 100, we have 200 minus 100. So the length is 100. So the width is 100, the length is 100. It's a square. Well, no wonder. I mean, it only kind of makes intuitive sense. Remember a few minutes ago we talked about the area of a really thin rectangle. You see, it wouldn't have very much area if it was really, really thin. And then when it kind of fattens out, it gets greater and greater and greater area, and it turns out that the maximum area turns out to be a square.